Yeah. Now, do you remember how to find the regression line in your calculator from here? Once you got your data in? You'll go to Stat, Calc 4, and that's the LinReg. Leave everything else blank, yeah. And you should then see an output that looks kind of like this. Yes? Okay, so if you don't have the R values, that means that you need to turn on some stat stuff on your calculator. Okay? Once you turn it on, you just leave it on. It's no big deal. So the way you do that is go to Mode, find Mode, and scroll up 2 or 3. Just use your up arrow, go 1, 2, 3. If you go up 3, it says Stat Diagnostics, and you want to make sure that's turned on.
Why is it off by default?
I don't know. And then the Stat Wizard needs to be turned on also. Your Stat Wizard is right there in the palm of your hand. You have the power. Turn it on, and then go back and hit LinReg again, and your output then should show the R and the R squared. Yeah.
You said our wizard needs to be
On. Stat Diagnostic and Wizard needs to be turned on. Then you'll have to go rerun your LinReg to see your R and your R squared, okay? Now, we're not messing with R squared yet. That's an after spring break conversation. R is the correlation we talked about yesterday, right? Did you guys get this output now? Yeah? We good? Okay. The nice thing is right now they're going to give you these equations, but if you need them, they're here, okay? So here it is. The line that best fits this data is this equation. Now, that's the way it looks in Algebra 1, right? But in stats, we have to throw in some extra symbols and context. Because we are trying to predict the distance that Barbie falls, right? By the rubber bands. So when we do that, we're going to call the y variable, instead of y, we're going to say distance traveled or distance fall. And I'm going to put a little hat on it. The distance traveled is equal to 25.333 plus 7.464. And instead of x, I'm going to put in the context, which was number of rubber bands. Now, why do we do that? Because this guy right here, this hat, the way we read that, you can say hat, but you can also say predicted. It's just a reminder that these regression lines are just prediction lines. They're not perfect, and these predictions are not completely accurate, right? They're just a best fitting line. So as we use this line, we just realize it's a prediction, that's all. So then look at number 2. Use the regression line to predict the distance that Barbie travels for 5 rubber bands. How would we do that?
Put it in the equation.
Put the 5 in for x, right? That's all there is to it. So my predicted distance would be 25.333 plus 7.464 times 5. And when I run that, I get 62.653 centimeters. Do we have to show work? Yes. You have to show work. I know the calculator's doing it for you, but you need to do it. Okay. So far, so good? So this is a prediction. Now it says one of the group members found the true measurement for 5 rubber bands was 64 centimeters. Was the prediction from number 2 that we just found, was it too high or too low? It's too low, right? You can see it's lower than the actual. And then by how far off? Well, if I take that 64 and I subtract the 62,653 we just found, I get 1.347. So it was 1.347 centimeters too low. The prediction was too low. Now, visually, what does that mean? Well, go back to scatter plots from yesterday, right? We'll say we have our scatter plot. And then we throw the best fitting line here. Well, that point would be right here, and the line, the prediction line, is right there. So the line is literally lower than the point, right? So this is what we call a residual. And what residual means is it's the distance from the actual point to the prediction line. That is what a residual is. And how do we find it? Just subtraction. That's all it is. Okay? Now, and also, what you have to be careful of is you always do the actual minus predicted. It has to go in that order. Because sometimes, think about it, if that point was below that predicted line, my residual would be negative, wouldn't it? So it's okay to get negative values because that just tells you the line predicted way higher than the actual value was. All right? So how do we remember actual first? Because it's an AP class. Clever, A. I didn't make it up. Always actual minus predicted. All right. Now it says predict the distance that Barbie would travel if the group used 20 rubber bands. Now we're just doing what? Plugging in 20, aren't we? Okay. So the distance would be 25.333 times 20. And I get 174.613 centimeters. Okay, so then it says, would you trust this prediction more or less than the one that we made for 5 rubber bands?
I say less.
You say less? You trust it less because why?
All of our numbers are pretty low.
What do you mean by all your numbers? Can you be more
All
specific?
the numbers we tested, like all the number of band numbers were pretty low.
Because it's like farther than 6 feet forward.
Yes and yes. All of that's true. Because look at the data that was collected to create the line. We didn't go any higher than 7 rubber bands, did we? 20 is way outside that data set. So the line only predicts well up to 7. Anything outside of that, you're taking a lot of risks because we really don't know what happens. Because maybe the data point goes down and now the regression line is going to have a negative slope. Or maybe it's going to make it curve. We don't know what happens beyond 7 rubber bands. So if you try to use that line to predict it, it's super unreliable. Obviously, if the point is really, really close to the data set, then it's more reliable than something that's way outside. Either way, though, it's called extrapolation, and it's considered unreliable. It's a really bad form to use it, okay? So let's summarize that, okay? We would trust it less, because 20 is far outside the data set collected. And this is what we call extrapolation. All right. When you predict within the data set, guess what they call that? Interpolation. Yep, interpolation. Makes sense, doesn't it?
And that's more accepted?
Oh, completely. Yes. Interpolation is fine. Within the data set is perfectly fine. As long as you realize it's just a prediction, it's not perfect. Okay. Now, little algebra here. Look back at our regression line that we got in number 1. What is the y-intercept of that line?
It's like 25.
Okay, 25.333. And then just for number 6, this is what's the slope? So let's pick out the slope while we're at it. 7.464, right? That's the slope. So that's algebra 1 in AP Stats. We have to put meaning to that number. So we get to do an interpretation. Your favorite, right? That's what makes stats different. We get to put meaning with the number. So y-intercept. So stop and think for a moment. Back in algebra 1, when you learned about y-intercepts, that was like the place where the x value is 0, isn't it? So we just need to think in those terms. In this case, x represents rubber bands, right? So if I have 0 rubber bands, what is the distance that Barbie's going to fall? 25.333. Does that make sense? That's all we're saying here, all right? So we would say if there are 0 rubber bands the predicted distance traveled is 25.333 centimeters. Now this is not saying as we throw her off the balcony, we're just saying if she's standing on the ground and she falls with no rubber bands, how far will she fall? Well, it's just her height, right? When we actually measured it, it was about 28 centimeters. So this makes sense. It's pretty close to the truth, all right? Now, when you do interpretations, though, you need to be really careful and make sure that you use the word predicted. Predicted. Last year, one of the rubrics was super strict about this. If you didn't use the word predicted, you lost a point. All right, now, let's switch gears and do slope. Let's see if we can put this in context. So, slope is connected to our x value, right? Okay, what did x represent in this question? Rubber bands. So we would say, with each additional rubber band, the predicted, here it is again, predicted distance traveled will, okay, increase or decrease? Increase, how do you know? Because it's positive, right? Will increase 7.464 centimeters. So we want to be really careful in this unit to remember to put units on our answers and use that fabulous word of predicted all the time, everywhere you can. Nothing is for sure, right? It's all predictions. All right. Questions so far? Yeah? Okay, let's summarize this and see how we do on the back. Okay, with predictions, there's our basic general equation. Okay, remember this little hat stands for prediction, right? Or predicted. A is the y-intercept. B is my slope. So you'll notice it looks a little different than Algebra 1. In Algebra 1, you said it's mx plus b, right? Well, in stats, we put the x term in the back because realistically, most things in life are not determined by one variable. There's a lot more variables, right? And so when we start adding on variables, we just add them all in one row. The constant, the y-intercept, just sits at the front, all right? Okay, now, so we want to write the equation in the context, or you have to define the variables to get the full credit, okay? You can't just say y equals something, something x. Be careful of extrapolation.
Would we be able to extrapolate it would we be able to, on the AP exam, extrapolate if we clarified it was extrapolation, or is it just like a no-go?
Depends on how they ask the question. They could say, you know, what's the predicted value for this, and would you use this, or why not? Then you would predict it, but you would say this is a bad idea because this is extrapolation, very unreliable because of, you know, blah, 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 blah. Just depends on how it's asked, but usually they're not going to ask you to do something that's bad form. It's just bad form in general. But they might say, hey, this person did this. What's wrong with his process? You know, and that's for you to pick up on. See that, okay? All right. Now with residuals, we said it's always the actual value minus the predicted value. All right. Now actual will be given. It could be given to you in the stem of the question. It could be given to you in a table. You could read it off a scatter plot or even something called a residual plot, which we'll see after spring break. That will be given in some form. The predicted you find, just like we did before, by plugging into the regression equation. All right? So it's usually a two-step process. You got to do the prediction, then do the subtraction. So then here's the interpretation. The actual response variable in context, right? So the actual fall of Barbie was whatever the residual is. 1.574 centimeters. Above or below here, the predicted value for x equals whatever it is we plugged in. Okie doke. All right, last thing, interpreting y or slope and y-intercept. So with slope, we say with each additional x in context, whatever x is, for each additional rubber band, the predicted y in context increases or decreases by whatever the slope is. All right, then we do this for y-intercept. When x equals 0, in context though, when there are no rubber bands, the predicted y in context, the predicted distance of the fall is y-intercept, whatever that is. So I would put a little asterisk, don't forget to put units on your answers. Centimeters, feet, calories, whatever it is. Okay? Don't forget your units. Okie doke. Now, try this. Try these application problems down here, and we'll come back and check them in a moment. We got plenty of time, so I want you to try them. All right. Let's see how you did.